My name is Schwenker, and I'm a graduate student in the Department of Material Science and Engineering. Today, I'm going to introduce to you this idea of using computers to see beyond imperfection. Now, this is not using computers to stare into the depths of your soul to see all of your imperfections, but rather, it's using computers to see imperfections that are present in materials. Now, probably nobody in the audience would admit to being a materialistic person, but we all have to acknowledge that materials are all around us. They make up every essential component of our world. Take, for instance, or just look outside a window at the beautiful downtown area of Chicago. It's a wonderland of steel, concrete, made possible through material innovations. Consider the arsenal of electronic devices that you now have. Those are made possible by materials innovations. Or think about electric cars. The ability to now travel 100 miles on a single charge, or a single charge. And finally, think about medicine. Today there's an effort to try to cure diseases like cancer by taking tiny materials and having them fight these diseases at a very targeted level. So all of these are very interesting applications of materials, and these are all different ways in which we experience this world. But how is it that we can see the materials world? Well, scientists have spent decades trying to think of how we can better use microscopes to zoom further and further into materials. And we've gotten to a point now where we can do a pretty miraculous thing. And that is we can actually see the atoms that make up the materials. If you think about it for a second, that's pretty amazing because atoms are the building blocks of everything. So these images here are actually, the bright spots you see are actually the atoms. So this is a very direct picture of the structure of a material. Why does that matter? Because structure is everything to us material scientists. And to you, because this is something probably very familiar to you, obviously, water and ice. Now, water is a liquid, ice is a solid. That's how you know it on a day-to-day basis. But if you ask a chemist, material scientist, or somebody that has access to high-powered microscopes, we can actually look at the structure of water and ice under a very high-powered microscope and see very drastically different things. So, if you notice, they're both composed of H2O, so H2O molecules, but water is a amorphous arrangement of these molecules. That's why it's a liquid. In the case of a solid, we have a more crystalline ordered lattice structure, and you can see that's what makes it a solid, or gives us ice. So we can see these atoms. Seems like a perfect world. We have a good understanding of this, but the reality is imperfections are everywhere at this level of detail. Now, my particular area of research deals with materials used for solar energy applications. And here we have pictures of solar panels. This actual image here is of a material that's used in solar panels. And I've been harping on this idea of imperfections. They're actually what make the materials most interesting and what actually keep material scientists like myself employed. This is what we're ultimately trying to do, is discover what effect these imperfections have on these materials. Because solar energy right now is not economically viable because of the fact that simply in order to make it work well, we have to buy hundreds of thousands of solar panels. So there's an efficiency problem. We believe that the solution to that problem is hidden in these images, and in particular into the imperfections. And I've highlighted some of the areas here in this specific image where the imperfections are. So what we do first to look at these actual materials in these images is we just simply stare at them. There you go. Beautiful, right? I'll even give you a little bit of help here and tell you what's interesting. There, that's interesting. So the way that we can use these images to find structure would be to, zoom in. Maybe that'll help us see in this area that we can't see as well. So we can do this, a little more clarity maybe, but we get to a point where we hit a brick wall. And at this point, science kind of has this very teasing way with us. We think that by going closer and closer, we're getting actually closer to the answer. But in reality, it's an abyss staring at us and telling us, what are you doing? This is ridiculous. So what I do is I use computers to help me better understand what's going on in these images. Specifically, I train them to help me see these images better. You're probably thinking, well, what can a computer do better than a human? I'm not here today to convince you of the strengths of computation versus a human, but what I will say is computers are very good at doing two very specific things. One of them is they're very, very, very sensitive. And you can imagine at this level, sensitivity is very important. This was a very interesting study done where a computer looked at a video of a human's face, and from that video it was able to detect the pulse. Now that's something extremely subtle that the typical, or really the human visual system in general, can't pick up on. In addition, once we train these computers to actually be able to see these images, this vision is a very scalable thing. We can take this and use it over millions of images. If I were to just hand you a million images, you would either throw them all up in the air, or if you're your computer, you'd probably toss your computer out the door, because it's just too much to process. So because of these two different things, computers are a very good candidate to help us understand what's going on in these images. Now, they aren't perfect, and this is an interesting case of where a computer is actually trying to see something that's not there. It's obvious to you and I that that's an image of a goose in a pond, but actually the computer decided that there was a car there. Now, that's not to say that there was actually a car in the pond. There wasn't. But if you take a look at the pixels, kind of looks like a car maybe. So this is a problem, but largely these types of problems can be alleviated by the way in which you train these computers to see. Now, I want to give you a very, very broad overview of how we train computers to see. It's a very interesting field, and you could do a whole talk on just this topic itself. But I think it's very useful to think of how we would teach a toddler to identify objects that are see. What you do typically is you point to, say, a puppy, and you say, that's a puppy, that's another puppy, that's a cow, that's a giraffe. And all the while, they're forming images in their head of what these creatures look like. And they're modifying them as they get more and more examples. Well, the same thing happens with the computer. We're giving it thousands to millions of images which we label. We very explicitly say this is what a cow looks like. And we have to do that millions of times, probably way more times than we'd ever have to do for a human. But the point is, after all of this training, the computer learns this very complex relationship between the image itself and what's inside the image. So, in my particular application, I'm not using it to identify different materials. I'm using it simply to look at two images and be able to tell, are these images similar or not? So a good example would be if the computer saw an image of an apple and an orange. They're not the same thing. There are some similarities. How do we measure that? How do we quantify that? So that's how I use computers specifically in my application. So returning back to the solar panels, this again is an image of a material for a solar panel, and we want to know the structure again. And this is what the computers can be used to help us do. So the very first step is we have a framework of software that we use to help us with this task, and it has the computer vision integrated into it. But the very first step is we have to start somewhere, so we guess. Here's our first guess at what the structure is. Now, from the guess of the structure, we simulate an image. And here we are, we're coming to the point where the computer vision comes into play. Because the computer has to tell, are these images similar or not? And as you can see, there's not a lot of similarities between the two. So in this case, what the computer would do is it would reject that match. Now, it rejects the match, so it has to start over and try something else. It tries a new structure, you get a new image, and again, there's not much similarity between these two. Now remember I told you that this vision is a very scalable thing. So a computer can do this thousands and millions of times very rapidly. So all these iterations, this is not really expensive. And so eventually we get to a point where we get a structure, and the computer is able to identify some similarity. In this case, it automatically identifies it. There's kind of this diamond-like structure in both images. And rather than reject it this time, what it does is it updates its guess. And it continues to do this until eventually it solves for the structure. Well, let's back up here. Remember, I said this is all about seeing beyond the imperfection. And in one sense, this is just a general definition for happiness in life. You can't possibly be happy if you can't look beyond the imperfection. But what I want to leave you with is this idea of what seeing beyond imperfection means for material scientists. So it's interesting, we have these images now of atoms, of imperfections, and we acknowledge that there is some complex relationship between what's going on in this image and some kind of deficiency in, say, our solar panels. Now, we use computers to help us better understand the structure of these, specifically the structure of the materials that are used to produce these images. And that's what makes the material scientist happy, is having that structure. Because once we know that structure, we can use the knowledge of the structure to help design better materials, and in this case, to help solve the issue of solar energy efficiencies. So that's what it is. It's about seeing beyond perfection. In some sense, that means being happy. But I want you to realize, too, that that's a way in which we can design better materials to have a better world we live in.